Okay, well, thank you very much. So I touched on some of these topics in the school, but in the opposite order. So I probably won't get to the last part, and so I'll mainly talk about graphene, especially given all the other talks that seems appropriate. Okay, so let me just begin by saying a few words about what I mean by quantum matter without quasiparticles. So, we've all studied complicated systems like spin liquids and fractional quantum Hall states, which are described by what you would say, loosely say, highly entangled many electron states. But these are all states, even though they're very complicated, they have quasiparticle excitations. So what that means is that if you perturb the system in some way, then for a fairly long time, you can describe the response in terms of particles that moving approximately in straight lines before they collide with some other particles. Scattering of impurities doesn't count. I mean, that's still the same particle, it's just wave function is changing a little bit. That's not an incoherent scattering event. But there are many systems, especially in correlated electron compounds like the high temperature superconductors, where the quasi-particle concept doesn't work in the experiments at all. And it's been a long-standing problem to try to understand these phases. So what I'm going to do today is actually talk about graphene as a toy model for us, or what people call a strange metal, or a realization of matter without quasi-particles. It's kind of marginal, but it turns out to be simple enough that we can actually make substantial quantitative progress in understanding what's going on. And then if there's time, I just may say a few words about other kind of rather artificial theoretical solvable models that actually inspired originally the analysis on graphene. But I won't, we'll see how far I get. Okay, so when I say I'm talking about systems without quasiparticles, that has the somewhat unfortunate definition of defining something by what it's not. What we'd like to do is define such a state of matter, but in some positive way. And one way that's gaining some currency in recent months, in fact, is by thinking in terms of what I called a long time back, somewhat loosely, a local thermal equilibration time, which is if you have a quasi-particle system and you kick it, eventually it will thermalize, but the thermalization time is of the order of the collision time between the quasi-particles. And in something like a Fermi liquid, that diverges as volume temperature squared, or in a gapped spin liquid, it will diverge as exponentially with temperature as temperature goes to 0. But there are systems which are near quantum critical points or so strongly interacting where there are no quasi-particles. And if you try to estimate how long this time would be, in almost all cases, essentially all cases, you come up with a much shorter time of order just h bar over kBt. It's curious that at this point, this c is a dimensionless constant. So, I left it a bit unspecified there because we didn't know, didn't have any rigorous argument. But anyway, I propose that this is, in some sense, a lower bound. There's this sort of, in the spirit of the Yoffie legal lower bound for elastic scattering. There's a lower bound on thermal equilibration and inelastic processes, and nothing can equilibrate faster than this locally. So this kind of idea has been kind of reappeared, but in a more precise and sophisticated context by people actually thinking about what happens near black hole horizons. I won't go into that right now. But they formulated it in terms of what they call the butterfly effect, especially Schenker and Stanford. And this is the idea is that you take a quantum system, you let it evolve in time, and then you try and make another experiment where you perturb it a little bit, that's the butterfly, and then ask how long before the butterfly has totally destroyed the state. And you can measure this effect by this out-of-time autocorrelation function, and after some fairly subtle and careful definitions, you can define the analog of Lyapunov exponent. In this case, it's the Lyapunov rate, lambda L, whose inverse is the Lyapunov time. And that's, in the spirit of this thermal equilibration. And again, through a different set of arguments coming from gravity, they argued that, in fact, this time is bounded by h bar over kBt again. and with the precise factor of 1/2 pi, which is turning out to be quite significant in recent work. And they were, be able to give an argument for this lower bound just on very general quantum mechanical analysis based upon analytic properties of this out-of-time order correlation function. Okay, so that's with that general introduction. The idea, of course, here is that graphene, near its direct neutrality point, provided it's sufficiently clean, and provided the electron-phonon interactions are weak enough. So those are all rather difficult conditions to satisfy. Then we think it should be a system, and this is something we argued many years ago, which is close to this bound. That is really of order h bar over kBt. Let's not worry about the 2 pi. In fact, in graphene, very likely there's also log t over here, so it's logarithmically larger, but okay, that's fine. We're not sensitive to logarithms. All right, so then, a positive definition of quantum matter quasiparticles would be systems that go chaotic in this many-body sense as fast as possible. Okay, so that's a general introduction. Now let me turn to graphene and more down-to-earth considerations. So I'm going to show you experiments by the group of Philip Kim and Casey Fong, I guess former postdoc, I think, but now he's at BBN. And much of the more recent theory was done by my student, Andy Loomis. Okay, so that's graphene. Don't need to show you this. And as a function of density and temperature, we can draw this kind of idealized phase diagram where when you're at low enough temperatures away from the neutrality point, then you have a Fermi liquid. You have a Fermi surface, electron Fermi surface here, and a whole Fermi surface over there. But right near the neutrality point, the Coulomb interactions, which go as 1 over r, and the kinetic energy, which goes as momentum, which is also 1 over r, differ only by a dimensionless number, the fine structure constant. And because of that reason, the interactions are effectively very strong. They're not suppressed by any screening effects. And up to logarithms, you expect quasiparticles to be rather ill-defined. And so we argue that this should be a regime where you should see some of these effects of realization of a state of matter without quasiparticles. So how do we think about transport? Now, of course, the real world is not this idealized Dirac fermions. The real world has impurities, the real world has phonons, and you have to then think about what does it mean to talk about transport in a system without quasiparticles. So this picture, I hope, will kind of make the basic point. So on the left is you have a system with quasiparticles. So the idea here is that you have a liquid you have what's called a Fermi liquid when you're in this quasiparticle regime. But that name is really a misnomer. It's really a Fermi gas, and because the things actually transmitting heat or charge or spin are very dilute at low temperatures. Most of them are well below the Fermi surface, and so most of the electrons don't matter. So it's really a Fermi gas of some renormalized quasiparticles, which basically move in straight lines, and every now and then they encounter an impurity, so that's an impurity there, and scatters off the impurity. And this impurity scattering event basically controls all the transport properties. On the other hand, if you had a system without quasiparticles, here's the mental picture you should have. Now this is really actually a liquid, like water is a liquid, rather than a dilute gas. The electrons collide with each other so frequently that really they don't, you can't even tell when one electron ends and the other electron starts. It's interesting to realize that, the theory of flow of liquids, hydrodynamics, was developed before the theory of molecules. So we don't really need molecules or anything like that to make sense of hydrodynamics. So here you have this liquid of electrons so interacting so strongly with each other, and in particular interacting more often and more frequently before they see an impurity. So that's, very rare event in solid-state physics, although now that we're understanding how to get it, it's seems to be present in a number of places. So you have this liquid flowing, which is really flowing around impurities. So to think about the effect of impurities, not in terms of some electron scattering of an impurity, which is unfortunately the way many theoretical analyses are done in other fields of physics, but really in terms of a liquid flowing collectively around impurities. So this would be, so I'll contrast these two regimes by calling this the ohmic regime of transport. And almost all experiments in finite matter physics are in ohmic regime. But now we're learning that some of them, either carefully arranged or unknown to us before, are in this hydrodynamic flow regime. So what is the characteristic of ohmic flow? Well, one of the striking characteristics is Wiedemann-Franz law, which is the ratio of the thermal conductivity to the electrical conductivity. So this is the kind of transport you have, and if your scattering is mostly elastic, you have quasiparticles, and the ratio of these two quantities is just a pure number given by fundamental constants of nature. And this number, the Lorentz number, is, okay, this is some plot we pulled out of a paper, is highly obeyed by just about every material at low enough temperatures. Over, a range of carrier concentration from 10 to the 18, 10 to 12, to 10 to the 24. Okay. So how would we talk about this kind of regime? How would we compute the Wiedemann-Franz law? So this is something we did in 2007, motivated really at that time, graphene, I was only dimly, I don't think graphene had really been studied very much in those days. We were motivated primarily by the high temperature superconductors. And this idea that there's an exactly solvable realization of a state of matter without quasiparticles, which is related to the behavior of black hole horizons. And from some exact solution of black hole models, we realized that actually there is a very reasonable way to treat this from a first principle basis, and that's to use hydrodynamics. So of course we know about hydrodynamics of water described by the Navier-Stokes equation. But here what you have to use, you have to modify it in two ways. You have to modify it by realizing it's a relativistic fluid, so that changes some of the aspects of the transport. And second, you have to modify by putting in impurities, which means that momentum conservation doesn't really hold, but nevertheless, momentum is well defined enough so that momentum is conserved longer than a quasiparticle is conserved. That's the condition for this to work. And so if you now look at those equations, which in the end are not that difficult to derive, once you decide that's what you need to do, we got this formula for this same ratio, the Wiedemann-Franz ratio, in terms of some basic quantities, like the enthalpy density with an H, the temperature, the Fermi velocity, the charge density Q, and then sigma Q is the conductivity of graphene right at the neutrality point at 0 temperature. And then finally, there's this tau imp. And tau imp is the effect of impurities. It's not the scattering time of an electron. It's not the lifetime of an electron. Electron lifetime is much shorter. Tau imp is the relaxation time of the collective momentum of the fluid as it scatters off the impurities. So that's the basic formula then. And among the features that you can see here, if you take the limit of a very clean system, that tau imp goes to infinity first, and this 1 over, okay. Well, if you take it very large, there's still a factor of tau imp that doesn't cancel, that's correct, but there's also a factor of 1 over q to the 4th. So in fact, it becomes extremely large. On the other hand, if you set q to 0 first, then this thing, tau imp goes to infinity first. You see, I get confused about it. There's an order of limits question on how you do it. But if you take a simple, okay, Lorentz, I may have made a mistake in some expression here. Square, that doesn't quite cancel. I don't know, okay. Actually, I have got to correct that. Anyway, so let's just focus on at a given impurity density, what happens as a function of Q. Then this thing has this Lorentzian squared form as a function of Q, and it's got a large peak at Q equals 0. So the point here is that if you have a completely pure system, then the thermal conductivity of a completely pure system is infinite at Q equals 0, whereas electrical conductivity is not. On the other hand, if you're not at the Dirac point for a completely pure system, then the thermal conductivity is finite, whereas the electrical conductivity is infinite. So there's a very strong order of limits question on whether you take the very pure system to zero limit first or then go to the charge neutrality point. And this formula correctly describes those crossovers, but I think some of these words I have to change a little bit. Anyway, so going back to this phase diagram then, so the idea is that this is the regime of quasi-particle transport. This is the regime of collective hydrodynamic flow. And now if you put in impurities in this phase diagram, you realize that you can't really, you expect this quasi-particle flow to reappear at low enough temperatures, because the collision time of the quasi-particles is h bar over kT. So as temperature goes to 0, that time becomes longer and longer, and eventually it becomes longer than the electron impurity scattering time. So if that's the case, then you're back to a Fermi liquid picture because the impurities have taken over before you lose the quasi-particle. So you have to be in the sweet spot above this temperature, and the hope is that, and I've greatly exaggerated this picture, and the hope is that if you go to this regime exists before phonons take over, which eventually happens at high enough temperature. All right, so that was the picture that was discussed by us about 4 or 5 years ago, and recently then in a couple of years ago, Philip's Kim group had this new method of measuring thermal conductivity by some Johnson noise thermometry, and this is one of their measurements as a function of density of electrons. What's shown here is the thermal conductivity, and the blue line is the value you would predict if you obeyed the Wiedemann-Franz law. So that's a very strong check on their measurements and their technique for extracting the electrical thermal conductivity, because at low temperature, the Wiedemann-Franz law at all densities is extremely well obeyed. So that, so it's exactly the value expected from you measure the electrical conductivity, you use the Wiedemann-Franz law that predicts the thermal conductivity, and that agrees perfectly with what they see. So that's at 20 Kelvin. Now if you raise the temperature to 40 Kelvin, again, it seems to work, but there's now clear deviation right at the neutrality point. And then you go up to 70 Kelvin, there's a deviation by, a factor of almost 15. And that's exactly and the density dependence is roughly a 1 over Lorentzian square. So that's, exactly the kind of thing this relativistic hydrodynamic theory predicts. Okay, so in the same type of plot, in this phase diagram I showed here, if you plot as a function of density and temperature, the ratio, thermal to electrical ratio in a color density plot, then you see blue almost everywhere at low temperatures, and that's the value of 1 with the Wiedemann-Franz law obeyed. And right in this intermediate temperature regime between the disorder-dominated and the phonon-dominated regime, there's this factor of enhancement of 15 to 20, just exactly where you expected it, near the neutrality point. So they've looked at this, of course, we've done a great deal of other analysis, which I won't go into, as a function of density, as a function of temperature, and really the whole theory is highly constrained. This simple theory that gave the answer doesn't, it gets the overall trends, but when you look at it more carefully as a function of density, it makes a certain prediction that the enhancement of the thermal conductivity would mirror the suppression of the electrical conductivity as a function of density. That doesn't quite work. So that we realized eventually was because we're treating the impurities like point-like impurities, and that model isn't quite right. And then we instead worked in a puddle model. So you just write down an equation of a relativistic fluid in the presence of some slowly varying disorder of some potential. You have the fluid flowing in this regime with viscous drag, and if you solve those equations numerically, you can basically fit all the data with reasonable temperature dependence of all the quantities. So I think it all seems to fit together, that there is a whole new regime of transport which is different from 99.9% of measurement of electrical and thermal conductivities in other metals. Okay, in the same issue of Science, there was another paper. This is actually a theory paper which makes the basic point of another way of seeing the difference between ohmic and hydrodynamic flow. So here's ohmic flow. So what you have is, imagine this is a sheet of graphene. You have a source here and a drain here. So inject current here, you measure it here. What is the distribution of current? Well, if you're in the ohmic flow regime, you can model this rectangle by a square lattice of resistors. So just make a square lattice of resistors and solve Kirchhoff's law with current coming at one point and going out the other point. But if you solve that problem, you will get this type of flow. Also, you can solve it by solving Laplace's equation, which is a continuum version of Kirchhoff's laws. On the other hand, if you have viscous flow, and this is kind of an idealized system without impurities, then in viscous flow, where you have electron-electron interaction and breakdown of quasiparticles before you see any impurities, then, okay, along the center, the flow is the same. But now what happens is that this, and this is absent in ohmic flow. There's a current flowing here. It drags the neighboring region to come in the same direction. Basically, some of the momentum that the current is carrying gets transferred to the neighboring region. That's the origin of viscous drag. This is totally absent in Ohm's law. Ohm's law doesn't have any such effect. A resistor flowing some current doesn't drag any current in the next resistor. So because of this viscous drag coming primarily from the dominance of electron-electron interactions, you can have this region also wanting to flow, and eventually then it meets an obstacle, so you get a vortex with the flow going in the opposite direction. So then the prediction would be that if you measured the voltage over a little region over here, in this side, the current is flowing this way, whereas here it's flowing the other way. So that's the experiment by Andre Klein's group. Here's a sheet of graphene. They inject the current over there, and then it, I guess, flows out this way. And they're measuring the voltage between those 2 points. So that's the RV, which is this voltage resistance that's measured there. At high temperatures, it's all positive. And at low temperatures, 100 and 200 Kelvin, right near the neutrality point, you see this negative non-local resistance. So that's consistent. This is a picture from their paper of this negative region here is this vortex-like flow coming from hydrodynamic transport. So this is quite a striking effect. It seems to be present, much lower temperature than we would have expected from our own, from Philip Kim's measurement of thermal conductivity. So it seems to be also, and also at densities much farther away in particular. So somehow what we thought was Fermi liquid perhaps isn't really Fermi liquid. I think these issues are not fully sorted out, but at least the general trend and where the effect is the strongest is exactly where we expected it. Okay, those are the few things I have. How am I doing on time? I have about 5 minutes left. So I think I'll just break here for questions, and then I can say a bit more for the people who weren't in my lectures last week about some exotic models that are toy models of this kind of non-quasiparticle, or realize some kind of non-quasiparticle liquid, quantum liquid. Oh, you don't have to clap. I'm not done yet. But any questions so far? Yeah. Right. I mean, so sure. I mean, this is just coming from solving Navier-Stokes equations. I mean, so to the extent you can certainly get Navier-Stokes equations. This is a plot of just a solution of Navier-Stokes equations of a charged fluid. Yeah. So if you took a Reisner from a black hole and looked at what happens, and you put boundary conditions like this, I'm sure you'll get this. That's not the difficulty is to put in impurities. But that's when there's been a lot of holographic progress in the holographic community in the last 2 or 3 years about how you put in impurities in a controllable way. But we can discuss that later. Yeah. Yeah. I think this is for graphene, I would say, because, well, yeah, well, I mean, okay, certainly at low enough temperatures, here, but here, graphene itself at the critical point at 0 temperature, the free field theory, the critical point is kind of free. It's just, you really had perfect graphene at 0 temperature, then the electrons are essentially free. Now, in more complicated quantum critical points, it is strongly coupled. If you go to low temperatures, then you'll have to start worrying about the impurities. And the effect of impurities on a strongly coupled critical point is not easy to figure out. And you may flow to some other possibly strange metal of some kind. So that's what, I mean, the graphene is not as strongly interacting as other critical points. But it seems to be good enough, at least in this intermediate temperature range, as we anticipated, to behave like a fluid rather than a gas of electrons. Yeah. Let's see if I remember. So I think there certainly is, if you look at, okay, that's not over here. Well, there's this huge extra, no, that's not. I think you start seeing the electrical conductivity become strongly temperature dependent at some point. I think that's where. Yeah.
So is there any characteristic length scale or something at which the gas begins to look like a liquid? Because
right, so it would be I would say that the length scale is h bar Vf over kT. But that length scale has to be shorter than the puddle size. Okay, if the length scale is longer than the puddle size, then you will get just the usual fermi-liquid transfer. So you want, so you imagine you have all these puddles, and the question is, in each puddle, do I think of electrons moving individually and scattering off the puddles, or do I think of water like flowing in the puddles? Those are the two regimes. And higher temperature is more like, because the electron scattering times become so short, it's really like a liquid flowing around puddles. And that's when you get strong violation of the Wiedemann-Franz law, and we can predict exactly how it moves. Yeah. I don't think they'll be any different. They should have the same behavior. Plasmons are at a very long wavelength. I mean, in 2D, they're not really gapped, but it should be pretty much the same. There could be, there is some, actually, so my student, Andy Lucas, has been writing some papers on this. I'm not involved. There's also, in a liquid, there's also sound mode. And that kind of gets turned into the plasmon. But so if you take the system small enough sheet of graphene, there may be a way of, by optical experiments, of seeing the sound mode, the first sound mode of a liquid like this. But no one's seen that. Yeah. What, sorry? Well, at small enough voltage, sure. Now, we haven't thought much about the nonlinear effects. I'm sure they're different. I mean, I think what many people would love to see in a clean enough sheet of graphene is turbulence. Here, this is just in one vortex. What if you saw a whole bunch of them and you saw turbulence? That's another dream. Okay, so that's a nonlinear effect. All right. Well, I'm out of time. I'm now in the question period, or that's all I have to stop?
We have had some question period, so you can use the question.
Yeah, okay, good. So there's still 5 minutes in the question period, right? Okay, so let me just, no, that's okay. Let me say a few words for those who weren't there yesterday of a toy model, which goes back a long time, of a system that behaves like graphene in two senses. One is that it doesn't have quasi-particle excitations, and two, that its low energy fluctuations are described by analog of hydrodynamics. So this model, in fact, lives in 0 plus 1 dimension, doesn't even have space. So, but there is something that's analogous to hydrodynamics that seems to appear in the description of its low energy properties. And that model, okay, since I'm out of time, I'm just going to write down the model to begin with, is this one, which is being called by many string theorists the SYK model for these papers here. And this is a model where you just have electrons on n sites, and then two electrons can move from any pair of sites, say it's site 5 and 7, to site 3 and 13 with some matrix element J, 3, 5, 7, 13. And this J is an independent random number. That's the definition of the model. Just pick this n to the 4th random numbers and then allow the electrons to move only in pairs. So if the electrons can't move by itself, it can only move by entangling with another electron. All right, so this model can be solved in the large N limit. And among other things, you find in the large N limit that it has no quasiparticles. The Green's function has this square root singularity at the Fermi level, independent of the density of the electrons. And this is some numerical studies confirming that. If you replace the electrons by bosons, hardcore bosons, you instead get what looks very much like a spin glass state. So this, if these were bosons, this is like a 4-spin interaction with random couplings, and that's the spin glass. But if you simply have fermions, they can condense, and they form this quantum liquid without quasi-particles. I'll skip all of that. Then what people have realized recently, this is too fast, of course, especially this remarkable paper by Amartya Sen and Stanford a few months ago, has started with the saddle point that we found in 1993, which gave this solution, and looked at scalar fluctuation, energy fluctuations about the saddle point. What are the quantum energy fluctuations about the saddle point? What is the effective action that describes it? And the effective action turns out to be something I actually thought about this in 93, but it seemed like a hopeless problem. And certainly, I'm glad I didn't spend too much time, because it's clear that I would not have come up with this very beautiful answer, because I certainly didn't know any of this stuff in those days. So it turns out to be something called a Schwartzian, where this F is some reparameterization of time, and it's also related to local energy density. And this action is some kind of zero-dimensional version of hydrodynamics. So if you take this same action in higher dimensions, do the same procedure, you expect it to get Navier-Stokes-like equations. Okay, and the remarkable thing is that this particular action is something you can also get starting from quantum gravity in 1 plus 1 dimension. So quite generally, a whole class of models of quantum gravity have exactly the same low energy action as this 0 plus 1 dimensional quantum model. Okay, so that's all I'm going to say. And let me just put up my conclusions. So what we've studied is, graphene is turning out to be quite a remarkable example of something we wanted for a long time, which is something that has a metal without quasi-particles. That's so common now in pnictides and cuprates that it would seem that's the last thing you want. But it turns out to be a metal where we can actually make some progress and quantitatively understand what's going on. And that's partly related to my answer to your question, because the underlying critical point is relatively simple. There's no doubt as to what's going on at short scales in graphene. And one of the fundamental properties of such systems is that they have this intrinsic thermal equilibration or Lyapunov or scrambling time, depending on your perspective, which is of order just this pure number, h bar over kT. Okay, thank you very much.